Okay, because the lambda calculus in this model here, Jeremy was saying a third meaning here, in the power set of n, the lambda that I'm using there has the properties of lambda calculus. And so that's why we can use a lot of information that we got in more formal way, applying it to these particular enumeration operators. And what I'd like to show you is that there's really an enormous family of enumeration operators that you can think of in terms of type theory, and some of you are interested in thinking about types. But it's just one step in type theory. I can also show you how to go beyond that and get more complicated examples. And I'll only be able to sketch it a little bit in the time we have this afternoon here. But the notion of a closure operator is a very natural thing that comes up in mathematics and logic all the time. For example, if I take a set of integers, because integers, sum of two integers is an integer, I can say, well, I can take a set of integers and just close the set under sums. So every integer I get there has to be a sum of sums of sums of sums of sums from the original set x. So for example, if I started with singleton 0, then closing under addition of singleton 0, I don't get very far. I don't get beyond singleton 0. But now what happens if I close under addition zero and 1? Well, that's not very surprising. 1 plus 1 plus 1 plus 1 gives you everything, so the closure there. But what happens if I close under addition, binary addition here, 0 and 2? Of course, I'm only going to get the even numbers. So there's a whole subspace of closed sets, and many interesting examples come up from logic. A very popular operation in logic is to close a set of axioms under all proofs using logical rules. Now notice when you're closing something off here, it'll always turn out to be that the set itself is allowed, and when you close it under addition, of course you don't eliminate the set x there, but you just add more to it in terms of sums there. And the same way with logical closure, if you take any axioms, then of course any axiom is provable from itself, so the closure under proofs of a set of axioms contains the original set of axioms and all the theorems that you'll eventually get there. And so these closure operators turn up in many different ways and have nice properties, which I've written on the slide there. And one of the first ones that we got here is in terms of our model here for lambda abstraction here. What this closure operation means, it says, take a fairly wimpy lookup table and find the largest lookup table that does exactly the same. Okay, and now why is that a closure operation? Well, there are two properties that it has to have. When you close, you have to retain the original stuff that you start with. But if you do it twice, you don't do any more. If you take a proof from a provable theorem, it's still provable. You may not know how the original theorem was actually proved, but your professor said it was proved, so you don't question it. Okay? A proof of provable things proof from provable things is provable. And so what about this lambda abstraction here? Now here's a case where there's no clash of free and bound variables. Because if I take this lambda expression here and say I have to substitute x in x, then that lambda reduction gives me wait, what did I say? Oh, no, I said the wrong thing here. Wait a second. Oh, yeah. If I take this bound variable x and substitute x every place that that variable occurred in this expression, I get this f of x, of course. And so that means if I take this operation and apply it twice, if you're forming the largest lookup table that gives you the answers you expected, doing it twice doesn't give you anything new out of it. And the verification of that is just that we agreed that lambda reduction here is correct, and so that shows that's a closure operation. There are many closure operations, and in fact the closure operations form a very nice subspace of the space of all continuous functions, namely the enumeration operators. And what we think of in terms of the closure operator is to think of just the closed sets there. So in particular, the collection, this is a good example here, the collection of closed things, starting with F's, where F is anything in the power set of n. Okay. In the power set of n. If I take all the things that can be closed off in this particular way from arbitrary sets in n, then this is a subspace of power set of n. But the way the topologies work out, you don't have to do any work, you don't have to go through a lot of definitions there. This is exactly the topological space of continuous functions from power set of n into power set of n. So lambda calculus in this enumeration operation interpretation makes the topology for free. So the range of any closure operation is a nice subspace of the power set of n. One of those subspaces is the function space itself, but there are lots of others, and this is a phrase that turned up and so often turns people off. We get a category of subspaces. In other words, the power set of n has this nice topology that I tried to explain. The subspaces inherit the topology, and if we look at the subspaces corresponding to closure operators, we get a family of spaces that forms a very nice category, and I'll try to explain why people call it a category. Category theory is a kind of algebraic type theory. And what you need in understanding this in a category is how one kind of space can be mapped to another kind of space by means of a suitable function in the category. And the categories can be very abstract. The spaces in the category can be really crazy. And then the functions that are needed there will take only graduate students in French in order to understand them at all. But it's just another example of a category. We have an easy example of a category here, which has lots of properties that we inherit because of the lambda calculus. So the closure operators, closure operator what we're doing is making a closure operator correspond to the space of its values. There are different ways of saying it. And of course, a closure of a closure is a closure. So all we have to say is that what corresponds to the closure operator are the closed subsets of that under the notion of closure, whatever notion of closure you're interested in there, where X is an arbitrary set and power set of n. Okay, so this is the range of the closure operator, and we're thinking of it as a subspace there. But the range of a closure operator already determines the closure operator, because for every set y here, the closure of y turns out to be the intersection of all the closed sets where y is contained within the closed set. And this works out very similar to properties in topology 2. The closure of a set is defined as being the intersection of all the closed sets containing it. And the same thing works out here with the closure operators, that the closure operator itself as an operator really turns out to be completely determined by its values there. If we think of the family of values as a subspace here, we can say, oh, if I'm trying to close things, now you can understand that from the point of view of logic there. Because what are the, for an axiom system, what are the closed sets of formulas? Those are the sets of formulas that result by adding a few more axioms and then taking all the deductions from it. In other words, the axioms themselves give you the smallest closed set, but if you take another set of formulas there, you use the axioms and the new things there, and you generate more things there. But the closure of a set under these kind of deductions is just the same thing as taking all the closed sets containing it, because that means you'll be taking all the different ways of generating from the given things and the axioms the conclusions there. And so I have to leave it to you as another one of those exercises, but just from what I have on the slide here, it's not difficult to prove that the closure of an arbitrary set is, in fact, the least closed set containing it in terms of the intersection of them there. So closure operators and a special kind of subspace are very, very closely connected. But if we stick to the lambda calculus notion, the category of subspaces here turns out to have a very, very simple way to explain in terms of lambda calculus. And so if you want to ask yourself, when you have one closure operator and are comparing it to another operator, what would it mean to make a continuous mapping from the closed sets of C to the closed sets of D? It turns out it means take some continuous operator and power set of n, take a closed set of C, apply this operator to it, and you get a lot of crazy answers, but you say, please close that now under D. And then you're absolutely certain that no matter what continuous F you start with, elements that are closed under C are necessarily closed under D by taking that composition thing there. But if you lambda abstract on that, lo and behold, that's easy to prove, is a closure operator. Let me do a little bit of that. So you see everything is monotone in these continuous functions here. So to say that x is contained in the closure of x is the same as saying that the identity function is contained in C as a continuous operation there. We're only working with continuous closure operator here, okay? And so if we take lambda f of D composed with F and its associative composed with C, okay, then we can argue algebraically by monotonicity that I could always replace each of the closure operators by a smaller one there, and this is lambda f of identity composed with f composed with identity. In other words, if you give smaller things here, everything remains monotone. It just gets smaller. But that's just equal to lambda f of f. But that's just equal to the identity combinator. So this combination of two things satisfies the first axiom about closure operators. Now suppose you do this combination twice. If you do this combination of twice, you're going to take D composed with D, composed with F, composed with C, composed with C. But C composed with C, that's the axiom of a closure operator. You can't do more than close it. C composed with C is itself. So D composed with D reduces to D. C composed with C reduces to C. So therefore, if you do this operation twice, it's a closure. So you see, once you abstract certain properties there and ask to which part of the space they're applying to, you can often get very simple sort of equational proofs in terms of this. So in other words, C arrow D is a closure operator whose fixed points represent all the continuous functions from the fixed points of C to the fixed points of D. So the thing is, you see, we're able to reduce types here. Instead of thinking about the space of continuous functions as a higher type function, we've actually been able to reduce it to thinking of a specific closure function. What's your question?
What's the fixed point?
You should know that. It's a point that's fixed, you idiot.
Did you mean fixed point, or do you mean just the range of
The range of a closure operator is the same as the set of its fixed points. That's another one, because in a closure operator, and this is a good thing here, you see, the algebra saves you a lot of effort there, because you can express things by less symbols there, because C of x equals C of x. So it says that the range of C of x is the same as the fixed points of C of x, because if you took any fixed point of C of x, any idiot can see that a fixed point of C of x is in the range of C. So the range of C is the same as the things. Question?
Well, this looks like you can use closure operators as retraction.
They're a kind of retraction, yes. They're a nice retraction.
This would be mapping retractions to retractions.
Yeah, yeah. And if there are certain kinds of other retractions that give you more interesting subspaces, but we don't have time for that. But exactly, you're taking the whole space and taking a continuous way of squeezing what things down into the things that you like, and so that's, yeah. Now, the same way that we did the function space, we can also do products there, because power set of n, and this is quite important for thinking about higher types there, we're reducing types as much as we can And we don't have to do pairs of sets of integers. Just by a little bit of arithmetic, the power set of n times, and as a topological space too, power set of n is really the same as the power set of n. Because every power set of n, every set of integers can be divided into its even and odd parts. And when you take the even part, you could just think of half of that. That's one set, and the odd part, you could think of minus 1 divided by 2. Every pair, every set of integers is in a one-to-one correspondence with a pair of sets of integers. And every pair of set of integers turns up that way. So power set of n, we don't have to make the types more complicated in order to have pairs. And now what we do with closure operators is to say, if I think of closing in terms of pairs, what it means, I think of the input as being a pair, and I close the first half of the pair by the one closure operator, and I close the other half of the pair by the other closure operator, and then make the pair out of the results there. And so that C cross D, that's a definition, and everything is continuous. These are lovely continuous enumeration operators, pair first and second there. And so whatever I write down there, whatever I write down in lambda calculus using enumeration operators is an enumeration operator. Now, will you be able to prove that C cross D is a closure operator? Can everybody see there will be? I said, you do the closure by thinking of the inputs as pairs of sets, and you close the first half and you close the second half. Well, if you take a pair and the closure, then the closure contains the pair, so certainly C cross D contains the identity function, but also C cross D composed with C cross D doesn't give you more than what you got out of C by itself and D by itself. So it's again an easy proof using lambda calculus and these definitions that the things are there. And we don't have time to work out all the formulas there, but what we have with the closure operators there is a category. We have a category of closure operators where F is a mapping from C to D, means F equals D circle F composed with C. But, so this is how you define a category. You have a certain bunch of spaces that you're interested in, and you say what it means to give a suitable function mapping the first to the second. And so I tried to explain to you how I got to this definition by thinking of the range of C and the range of D, that that's the right way to write it in the lambda calculus. But then category theory introduces, you often see it in the book, the home sets, because they worked in algebra originally. The home set is the set of continuous functions, the home set, C to D, is the set of continuous functions, that map C to D. But we don't have to go to a higher type here of taking a family of functions here, because we can just use C arrows D to represent the Hab set, because it will have the right fixed points, is this lambda expression, lambda F. In other words, we abstract out the function variable there, and we've represented the space itself, not one particular mapping, but the space of all the possible mappings from C to D. But now we also have products of things. And of course, maybe some of you have gone to some category theory lectures. Function spaces and products behave very nicely there because, for example, the function space from C to D0 cross D1, if I take a continuous function that takes on pairs of things, it might not be the same space, and you have to be a little bit careful to figure it out, but it's a topologically equivalent space there that you get simply by taking the functions into the first coordinate times the functions into the second coordinate. There are a million of these relationships between function spaces and products and things like that that are important categorically, but also have simple logical explanation here, which we can work out in lambda calculus. Now I had to put isomorphism there, and I'm not 100% certain what I really needed, but I did it because there are two different data types here. I'm taking mappings to pairs, and I'm thinking, is that the same as pairs of mappings? Well, maybe it's not exactly the same, but you can find two continuous functions that take data structured this way and turn it into data structured this way without losing any information, because you can go backwards and taking pairs of these things and get a pair mapping into pairs. So very often you have to use functional programming there to say things of one type can be rearranged to be things of other types. And if you get it so it's a setup, a one-to-one mapping there that's inverse to each other, then you have the isomorphism between the things. And there are many interesting laws of category theory that are similar to that. Question, whether there's a question? Someone raised a hand.
Maybe there's no question.
What?
So Dana,
You have a question.
or a comment, so about what we just did. It is actually kind of this really interesting sort of almost reflective thing that we just did. We just described the types for a language. So we're trying to, in some sense, describing types for like a lambda calculus, but we did it in the lambda calculus itself. So it's this very sort of circular kind of thing that just happened. And so each of these closures is describing a type. We could have, the ones you had up on the board earlier, like the even numbers, and that's a type of values, all the even numbers. Then the arrow constructor for talking about functions, you could combine that from two other closures. So you could describe the functions from even numbers to even numbers would be, we're putting the C arrow D, that would be even arrow even, would give you all the functions from even numbers to even numbers. And this gives you a way of sort of carving out and describing what Dana was calling subspaces of all the lambda programs.
This is a mind-bending example here, because any stupid function can be turned into a closure function there, because you can think of the function as being a one-step proof. What can you do with a proof of length 1? Okay, so when you go from x to f of x, you're just adding to x what you can do in one step. And so if you have the time, you can say, let's iterate starting with x, taking f of 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 anything. Okay? And so if you iterate that, any enumeration operator generates a closure operating there by thinking of the enumeration operator as just being a one-step proof, and then you just keep going, doing it over and over again. Of course, if you started with a closure operator, you wouldn't get anything new, because the closure operator gives you all the answers you'd get, and you could sort of say, I got it all in one step, don't bother me anymore, and so you wouldn't get anything new. So now if you turn this observation into a functor, then there's a universal closure operator. This is what's mind-bending because the types are all getting reduced to the power set of n. There is a closure operator that has all closure operators as its fixed points, but it is a closure operator, so lo and behold, it's its own fixed point. You could prove all of that by simple-minded, a little bit of set theory, taking into account monotone properties of union and lambda calculus here. So there's a universal space of spaces, and it has some fun that you can do with it. So I'm going to do the last thing here. I'm skipping over one slide because we're running out of time. You remember that the model of power set of n doesn't satisfy all the axioms of lambda calculus, because when I take lambda x, f of x, this is a closure, so it isn't equal to x, it's a closure of x. And so we don't have all the axioms of lambda calculus. We have a slightly weaker theory which has more beautiful properties if you bring in the lattice of unions and intersections of things there. There's more to lambda calculus than just combinators. May Curry rest in peace. And so we don't get a model where that's an equality there. If you want to get a model where that's an equality, what you can do is find a subspace by saying, hey, you said that forming the arrow function space there was a continuous operation on closure operators. Okay, if I have closure operators, then C arrows D by that lambda expression that I use there is another closure operator. And all of these are done in lambda calculus. So all of these things are enumeration operators. So the question is there a closure operator that is in fact identical to the closure operator representing its own function space? Maybe I should say here the range of the identity combinator is a whole of power set of n. But the range of I arrows I, which would correspond to the closure of the function space, is only a proper subset of power set of n. And so I is not equal to I arrows I, but maybe there's a non-trivial closure operator, which is, if we could find that, then we could restrict attention just to the sets in n that are in the range of D, and every one of those could be just as well as thought of as a function on D, and you'd have a perfect model for the lambda calculus with the extra axiom where this turns out to be an equality relation there. And so I just say how I did it there. You see, if you take D arrows D, then you can invoke close to take any crazy function and turn it into a closure operator. So I can now take the fixed point of the process that goes from D to the closure operator corresponding to D. So the fixed point will give me a fixed point of close. Everything is a continuous function. I just carry on using lambda calculus. And so the y operator gives me a D that's a fixed point as advertised. But now you say to yourself, wait a minute. I programmed it so that I know the answer is a closure operator. Everything in the range of close is a closure operator. So I know that's a closure operator. If D is known to be a closure operator, then D arrows D is known to be a closure operator because I wrote that proof on the board. So if I knew that was a closure operator, then close doesn't do anything more to it. It must be equal to D arrows D. But I had to do the things in those two steps to make sure that I know that everything I see here is in fact a closure operator. And now, as I say, there's a little exercise there. You can find in the range of D the empty set and the whole space quite easily in that. And so you'll find out that this is a non-trivial closure operator. So this is a non-trivial subspace of the power set of n, which satisfies all the axioms of lambda calculus. The power set of n slightly fails in one of the axioms of lambda calculus, and I don't think it's an important failure at all. But if you're one of those nitpickers who say, no, I want that axiom of equality there, I just gave it to you. Now I have to jump on a little bit, and I'm going to try to do it not too painfully here to get the next things here. Closure operators give very nice structures. The range of a closure operator is a partially ordered set which is closed under limits, and it's really like a closed set in some ways. It's very, very nice, but the closure operators only give some of the subspaces of power set of n. And the question is, might you be interested in others, and is there some kind of way of using lambda calculus and some logic about the properties of them that might be useful for formalizing semantics in this? So here is the idea that many, many people have used, and of course it goes back a long way. When you construct the real numbers, every real number is the limit of rational numbers, and so every real number can be represented in many different ways as a sequence of rational numbers, those sequences which do in fact converge to a finite limit. Okay? But many different sequences converge to the same real number because you can converge from the left or you can converge from the right, or half of the time you're on the left and the other half of the time you're on the right. You can set things up to drive people crazy that way. So there are many different convergent sequences that correspond to the same real number. So the Cauchy construction of the real line is to take, by using simple-minded rational arithmetic, say which sequences of rational numbers are convergent in a bounded way so that you know it has a finite limit. And then you divide those sequences into equivalence classes according as the two sequences converge to the same limit. And you can write that all down in rational arithmetic, the ordered field of rational numbers. You can write down what it means for two sequences to be converging to the same limit. So you construct the real numbers by first starting one type that is easy to understand as countable sequences of rational numbers, just ordinary sequences of rational numbers, But then you get the real numbers themselves by an equivalence relation, which is necessary because a real number doesn't determine which rational number converges to it. It shouldn't. But if you have a convergent sequence of rationals, you have a real number. So we can do the same thing with the topological space of power set of n. We can take quotients of subspaces. So now we just review what we already said there. The power set of n is the same as the square of the power set of n. Every element of our space could be thought of as a pair of elements of our space. And so every subspace of power set of n could be thought of as some kind of relation, a binary relation, depending upon whether the pair of sets belongs to the subspace. But now some of those binary relations could come up in the same way that we constructed the real numbers, because we can easily represent convergent sequences of rational numbers as just a set of integers, because you can number the rational numbers very nicely and do all the arithmetic nicely. So forming the real numbers is taking a relationship that gives us the equivalence relation between the nice kinds of sequences, which could be represented as sets of integers if we did all the arithmetic that was necessary to set that up. So partial equivalence relations give us an idea of type that includes hundreds of examples from mathematics. Have you thought any time about group theory? Do you know what a free group is? Well, of course, group theory has a certain notation for elements there. And what you can do is construct it syntactically by saying, let me take a group combination of products and inverses there, and then use the group laws to show that one combination is equal to another combination. So that means you're taking an equivalence relation on the syntactical space of group expressions. And that's the way you form the free group, by starting with variables, generators, and then you take all the group operations and inverses however you like, but you have to divide them into equivalence classes, because the axioms of group theory say, for example, the binary operation is associative, and the inverse undoes itself, and there's a number of things you need to put in there. It's done over and over again to think of a data structure to represent what you want to get at, but then you're forced to say when two of these data structures represent the same idea. And so we do that over and over again. So I'm just going to do it in an abstract way here of saying a binary relation that's a partial equivalence relation, that meaning it's symmetric and transitive. And of course the subspace is just the space of elements that are related to itself. But what I'm really thinking of is taking those elements and dividing them into equivalence classes. We have to be a little bit careful with types here, because things can get a little bit messy. So I'm not actually going to take the equivalence classes. I'm only going to work with the equivalence relation as a kind of generalized equality there. And I don't really need identity, because I just work with the idea of sameness in terms of equivalence there. Now, for example, every T0 space with a countable basis can be embedded into power set of n as a subspace, because you just have to enumerate the basis elements, and then you can associate points with sets of subscripts of the basis elements. I don't have time to go into it, but it's a very easy proof that was proved when I was only 4 years old, but not by me. A closure operator can give you a subspace there by simply taking the equivalence relation on the subspace there about the closed sets, and so that's a nice one too. But now I'm going to generalize from the closure operators, which are specialized subspaces, to the arbitrary kind of subspaces we can get out of partial equivalence relations. And we'll see how it works out and how the lambda calculus can be employed there. So here's the first definition. If I have two partial equivalence relations A and B, what does it mean to say that two functions are equivalent? Well, I say the answer is two functions are equivalent if equivalent inputs give equivalent outputs. That doesn't sound too hard to follow, does it? I mean, the structures I'm working out here are using a subspace of power set of n and then a sameness or equivalence relation on that subspace. Now, what would it mean to have a nice continuous mapping between two of these partial equivalence relations? It means equivalent inputs always give you equivalent outputs. Now, there's a logical problem here. Is that binary relation symmetric and transitive? You have to do a little bit of proof in predicate calculus. I wouldn't want ever to teach predicate calculus again because most of the theorems in predicate calculus are excruciatingly boring. Who cares whether for all x for all y is equivalent to for all y for all x? I mean, those are just boring theorems. But when you define things using relations and quantifiers, you may have to dig up some proof from predicate calculus to show, is that a symmetric relation? Why can I interchange f and g in that relation? It's written from left to right, f on the left and g on the right. So why is it symmetric? Because the a part is symmetric, I can interchange the x and y on the a, and the b part is symmetric, so I can interchange it, and then I can rename x as y and y as x. That's a step of proof of balancing variables in predicate calculus. And so it is a symmetric relation. Now I'll leave it to you to figure out what principle of quantifiers and predicate calculus show that's a transitive relation. There you have to go from A to B to C. No, I'm sorry, you don't have to do that. You have to go from F to G to H twice under that definition. I was getting ahead of myself there. And you need to juggle the variables in predicate calculus style to show that's a transitive relation. So this is our first notion of type here, that the function space is a partial equivalence relation. And in particular, Jeremy wanted me to emphasize, we get some polymorphism from lambda calculus here because the constant function k, that one combinator has an infinite number of types because it's always correctly a type that maps A to B to A. The constant function takes something in A, doesn't care a twig what's it's in B because it gives back the same value in A. So the combinator K is polymorphic in thinking of these types here. Jeremy, I'm getting really tired. I have to see. Oh wait, how much leeway do we have here? Oh, we have pretty much.
Or sit down.
I wanted to sit down. Oh, I know. There are some high chairs outside. Yeah, if I get a high chair, I'll be able to sit down here and do it. Now, you see both with the closure, first with power set of n, and with the closure operators, working with pairs turned out to be very easy and the pairing are all enumeration operators, and everything fits into the lambda calculus. But now if I think of these partial equivalence relations, I'm going to have just an easy time there, because if I take two equivalence relations there, I can think of the equivalence relation between pairs. And can you bring me a beer too?
Yeah, beer, which IPA. Okay.
Ow. I have a little bit of arthritis. Every once in a while it acts up there. So you see, it's really the same as we did with the closure operators, because in fact, if you think of a closure operator as the partial equivalence relation that's the identity function on its range, then this will be the same pairing to give you the notion of product type there. So if I have two types, A and B, then of course I do pairs according to A on the first coordinate and according to B on the second coordinate. Sums, of course, it means I have to take disjoint copies there, and there are many ways you could do that. But one way to do it is to use singleton 0 and singleton 1 as two distinct objects. So you take the copy of the first kind by taking pairs with 0, and you take the copy of the second kind with taking pairs with 1, and so you can say, oh, either I have taken something with a 0 or I've taken something with a 1. What did I take? Well, look at the second argument of the pair, and it will either be in the A or B depending on you do it. So this is better than with the closure operators, because this is disjoint sum. We take disjoint sums of structures, data types all the time, because we're saying I want to take men or women, if you'll forgive that sexist comment there. We take disjoint, I hope disjoint, no, sorry, don't listen to me, copies of those. Now, once you get these operations on types here, you can use your lambda calculus, and this is really just functional programming of the most basic sort. For example, take one of the things there in the middle there, I know, on the very last line there. I did that first one, but do the second one. If I take disjoint copies of A and B as functions into C, then any continuous function is made up of two pairs, two parts of a pair. The first is a continuous function that maps A into C, and the second is a continuous function that maps B into C. But of course, if you look at the data types on the two sides of that, they are different, but they're in a one-to-one correspondence, because any student can write the functional programming that transforms one data kind into the other data kind, because you just have to have the functions that tell you what the parts are, and then you have to have the functions that allow you to glue the parts back together. That's how you represent one kind of data as another kind of data. So there are millions of theorems like that to do with these. Now, we're not going to have too much time to go further with this, but this really kicks us up to a higher type notion, because we want to think of not just particular types one at a time. We want to think of types that depend on parameters. And so I'm going outside of power set of n. The types that I wanted to think about, the quotients of the subspaces, kept me inside of power set of n. But if I want to think of parameterized families of types, I have to go up to a higher level of mappings, and no longer in our lambda calculus model there. This is definitely a higher type. Mappings on the whole power set as a set of possible parameters into types. And types are subsets of power set of n. So again, we're at a higher level there of sets of sets of sets. But I don't think I have to go beyond sets of sets of sets. And I really don't have to go beyond sort of basic logic of quantifiers and lambda calculus. The lambda calculus comes in with this functional programming thing that allows you to operate on the elements there. But then the question is how you put them together to say how you want to have a structured type of some kind. So here is the first one that's the so-called dependent product. So a family of types could be indexed by a function there, and now B is a higher type thing there, but B of X is a type. Script T there are the types, and I'm thinking of parameterized families of types. So I say that it's coherent, indexed by A, if equivalent parameters from A give me equivalent types. I said equal types there, but I could have written in predicate calculus to saying, for all x0, x1, if x0, a, x1, then for all y0, y1, y0 is equivalent modulo b parameterized by x sub 0 to y1, if and only if y0 is equivalent by b x sub 1 to y there. I could make it look much more like predicate calculus if I say I'm thinking of relations indexed by variables which depend on other relations as to how you want things to fit together. So now, what does it mean to have the possibly infinite product of types? It means two functions are related by pi mean equivalent inputs give equivalent outputs, but I have to sneak into the whole thing the parameter that B controls. See, B is a higher type thing of giving you families depending upon things of type A. And so I have to say, if two things of type A are the same, then f of x, once I know what x0 is, should give me the same thing as f1 of x1. Now again, that's an asymmetric definition, and you need some more predicate calculus to prove that that's a reflexive and transitive relation. See, even though I went up to higher types there, I still am just using quantifiers and the way I've been doing all day here. And I just need to give the proofs that we get the nice properties of these relationships. So that's the dependent product. You see, for example, A could be the type of all singleton integers, just thinking of n itself. And then B of singleton n could be the nth iterate in terms of some kind of closure operation or some kind of other thing there. And so pi over n of the B of n's is an infinite product. So there are lots of mathematical constructs you can think of that could be defined in terms of dependent products, which means that when you're taking the answers there, as your parameter changes there, the range that you have for the value of the parameter has to change as well there. And there are many, many examples. Jeremy.
I've got an example prepared. Would it be a good time for that? The vector or tuples of a certain length?
Yeah, go ahead. One last remark there at the end of the thing there. Pi and arrow give you the same thing because by this definition, the product over A of a constant family of types means you don't have to worry about that extra parameter there. That's just the function space A arrows B. In other words, products give us exponents, as we know from arithmetic. Products, iterated products, give us exponents. And so I really should think of that as B to the A, and it's a product A times, so to speak.